Welcome to the next lecture of digital communication. Today we will study something called differential entropy. So till now you have done entropy for a discrete source. So you have a discrete random variable x with some probability mass function px of x, and you define h of x as minus summation over all x px of x log to the base 2 px of x. Now if x, rather than being discrete, if it is a continuous valued random variable, how can we define entropy? So without going into any details, I will directly use an analogy that whenever we have a summation in case of discrete, so in case of continuous analog we have integral. So we define equivalently entropy for this case in this way. So minus integral, and then this x is a continuous random variable. It has probability density function fx of x. So instead of px of x, we will write fx of x. Rest will be same, log to the base 2 fx of x. Now here will be dx. Now this entropy is denoted by small h of x, and this is given a name differential entropy. Okay, nice. Now here is an important very important result about differential entropy, that is, before that we can equivalently define relative entropy or KL divergence for continuous case also. KL divergence, I will recall. Suppose you have two random variables x, which is having distribution fx of x, and you have other random variable y having probability density function py of y, fy of y. Then differential entropy, relative entropy or the divergence between fx and fy, this is the notation. So if you recall, from discrete case you had a log of, then there was a py, here we have fy of so I will write here x for clear reasons. This is just a dummy variable, fx of x, again fy of y, and instead of summation there will be no integral. Okay, dx. Okay, so we know that this relative and entropy is always non-negative. This result we have in fact proved. We can prove it in the similar way, so there is no difference at all. And let's now compute relative entropy of some famous distributions, out of which we have Gaussian distribution, Gaussian random variable, okay, with probability density function 1 over root 2 pi sigma square e to the power minus x minus mu square divided by 2i sigma square. Now what is the relative entropy of Gaussian distribution? So we will use definition. h of x is integral from minus infinity to infinity fx of x log to the base 2 fx of x dx. Okay, so this will be equal to minus integral 1 over root 2 pi sigma square. So I will skip a little bit algebra. Okay, so it's a very simple step. I have used log of AB is equal to log of A plus log of B. This is your A, this is your B, and we get this result. Now log of 1 over root 2 pi sigma square is minus log of root 2 over sigma square. So this will be minus minus plus. So 1 over root 2 pi sigma square then times log of root 2 pi sigma square integral e to the power minus x minus mu square divided by 2 sigma square dx. You have to be very careful in evaluating this. If you will do it blindly, you will get stuck. There will be a lot of mess. I will just try to combine some terms in a way so that they become a very well-known integrals. Now what is log of e to the power a? This is simply a. So this part will be integral, this will be minus x minus mu square divided by 2y sigma square e to the power minus x minus mu square divided by 2y sigma square dx, and here is 1 over root 2 pi sigma square. Now see the first observation. I will write here log of under root. I can write 2 pi sigma square to the power half integral 1 over under root of 2 pi sigma square e to the power minus x minus mu square divided by 2y sigma square dx plus, oh sorry, there will be minus of this, and then integral, it will be now x minus mu square and 1 over under root of 2 pi sigma square e to the power minus x minus mu square divided by 2y sigma square dx, and here is 1 over 2y sigma square. Now look at this carefully. So first of all, log of a to the power n is n log a, so half log of 2 pi sigma square. This I can write again as fx of x dx, right? And then minus 1 over 2y sigma square x minus mu square. This again I can write as fx of x. This is the PDF of Gaussian. Now what is the integral from minus infinity to infinity of any PDF? 1. So similarly 1 by 2y sigma square. What is this? This is nothing but expected value of x minus mu square, which is variance sigma square by definition of variance. Okay, but I have done one mistake. I will now correct that. See, the log we are taking here, we have to be very careful. It is to the base 2. Now log to the base 2 e to the power a is a log e to the base 2. That we have to be very careful. So I have missed one term here. So there should be everywhere log e to the base 2. Log e to the base 2. So that will come out here, log e to the base 2. So log e to the base 2, right? So now sigma square gets cancelled out. So it is half log 2 pi sigma square minus log e. Both are to the base 2. So somewhere, oh, we have made some mistake. Let me be very careful. Yeah, the mistake is there is a minus sign here. Okay, and so there will be minus sign here. Then there will be minus sign outside and inside, which will become plus. That is a mistake. Okay, so it is plus plus plus. Okay, so now it will become half log to the base 2 pi e sigma square. So this is the differential entropy of a random variable which is Gaussian distributed with mean mu and variance sigma square. So one thing we see that it doesn't depend on mu, and it should not, because see, Gaussian distribution suppose is centered around mean mu. Mu does not affect the uncertainty. What affects uncertainty is this width. If variance is very high, then your distribution looks like this. If variance is low, your distribution looks like this. And high variance means high uncertainty. Okay, because there is an uncertainty, and then it takes large number of values. And low variance means low uncertainty, which directly affects the notion of entropy. High entropy means high uncertainty, hence high sigma square. Low entropy means low uncertainty, hence low sigma square. Okay, so we have found the Gaussian distribution and differential entropy for Gaussian distribution. Now coming back to this, d of fy fx, which is defined as fx of x log of fy of x divided by fx of x dx, and we know that it is greater than or equal to 0. Now we will do one thing. We again have, suppose, a random variable x, okay, which is distributed according to Gaussian distribution, and till now you must be well aware of the notation also. Gaussian distribution is also denoted as this n for normal, mean, mu, variance, sigma square. Okay, and we have another realization of this, another belief about a distribution of fy. Fy is unknown. That is any distribution. It can be any PDF. Okay, so now let's compute relative entropy when fx is Gaussian and fy is any distribution. So we don't know which distribution it is. It can be any other general distribution. Okay, so we write it. So fx is fx log of fy divided by fx of x. Nice. So I will not change anything here, so it will become log of x fy of x dx minus fx of x log of fx of x dx. What is this quantity? Okay, so this is simply h of x, so it becomes fx of x log of fy of x dx, and this becomes plus h of x. And we know the value of that h of x. Oh, I have made one mistake here. So if you see the definition, d of if you go back, d of p q, which is summation p log of p by q. So what we write here should appear at here, this point. So fy, so I'm sorry, so this is fy here. That is the only change we will have, fy. fy. Okay, then we are wrong here. So let me erase it. Okay, so actually this I can write as minus fy of x log fy of x dx minus, so this is now fy here and fx here. Okay, so minus fy of x log of, and fx of x is 1 over under root of 2 pi sigma square e to the power minus x minus mu square divided by 2y sigma square. Sorry for, I will repeat. Okay, no issues. See, you go back to the definition of divergence for discrete case. You had two PMFs P and Q over X, and then differential entropy between P and Q was P of X log of P of X divided by Q of X over all X. Now it is integral, now it is differential entropy between Fy and Fx, two PDFs. So it will be integral, first of all, Fy of X log of Fy of X divided by Fx of X. So that is what I have written here. Okay. So now what will be this? This is indeed minus h of y, entropy of y, right? And let's now see the right hand side, minus integral fy of x, right? And it is now log of 1 over under root 2 pi sigma square minus x minus mu square divided by 2y sigma square. I have just applied the formula log of ab is equal to log of a plus b. And the other thing I have applied is, we have to be very careful, log of e to the power minus x minus mu square divided by 2y sigma square. This will be minus x minus mu square divided by 2y sigma square. See, base is 2, so it is log of e to the base 2. So there will be this part here, log of e to the base 2 dx. Okay. So this is a minus h of y. Now the first part is log of, again I will write it 2 pi sigma square plus here integral fy of x dx. Okay, minus will become plus 1 over 2y sigma square log e to the base 2 here integral x minus mu square fy of x dx. See, we are talking of two distributions, but the variance of both distributions will be same. That is very important. So first will be minus h of y plus log of a to the power n is half log of 2 pi sigma square. Okay, integral minus infinity to plus infinity fy, that will be 1 because it is in a PDF. Okay, plus log e to the base 2 divided by 2y sigma square, and this is clearly variance, that is sigma square. Okay, because both will have same variance. So it is minus h of y plus half log of 2 pi sigma square plus log e, which is minus h of y plus half log of 2 pi e sigma square. Now this is the value of relative entropy between fx and fy, where fx and fy are two distributions of a random variable. They have same variance, same mean, but fx is Gaussian, fy is unknown, that is minus h of y plus half log 2 pi e sigma square, and this we know is greater than equal to 0 because differential entropy is relative entropy is greater than equal to 0. So it means minus h of y plus half log 2 pi e sigma square is greater than equal to 0. That is h of y is less than or equal to half log of 2 pi e sigma square. What does it mean? See, right hand side is it is the differential entropy of Gaussian random variable, okay, and y is any other random variable but same variance, okay, same mean and variance, but any so y will have any distribution. So it means among all distributions, the maximum entropy of Gaussian random variable, the maximum entropy possible for any random variable is when the random variable has distribution Gaussian distribution. In other words, see what I will write, that Gaussian distribution is entropy maximizing distribution. What does that mean? Suppose I have h of y is any random variable, I want to maximize it. What y will maximize this entropy? The random variable which will maximize this entropy will be the one which is having Gaussian distribution. So you can maximize, if you want to maximize this entropy, you need to take y as Gaussian distribution, mean that will have the maximum entropy. So this much for this part of lecture, and now we will use this concept to define channel capacity of Gaussian channel in the next lecture.